you very much for inviting me to speak to the Swedish SPR. As we were in Oslo, it was raining like this. And as you know, in the origins of parapsychology is shamanism, and a large part of that is rainmaking. So we just brought it with us. I'm going to talk about physics and the non-local mind. A couple of weeks ago in the popular science magazine, New Scientist, there was this article talking about an article that Lucienne Hardy, a physicist at the Perimeter Institute in Toronto, Canada, wrote. And so the article says, a classic quantum test could reveal the limits of the human mind. A Bell test experiment using something unprecedented, human consciousness. So a Bell test was referring to John Bell, the Irish physicist, who came up with a way of demonstrating one of the predictions of quantum mechanics that Einstein called spooky action at a distance, talking about entanglement. And it goes on to say, if such an experiment showed deviations from quantum mechanics, it could provide the first hints that our minds are potentially immaterial. So that's exciting. The article then went on to ask Nicholas Geeson, who's a prominent physicist at the University of Geneva, what he thought about this proposal. And Geeson said, if somebody does the experiment and gets a surprising result, the reward is enormous. It would be the first time we as scientists can put our hands on this problem of consciousness. To which I would reply, yes, but only if you ignore 150 years of parapsychology research. Because in many ways, what parapsychology has been about is trying to understand the nature and the capacities of consciousness. We give labels like telepathy and precognition and so on because we don't know what else to call it, but all of it clearly has something to do with consciousness. So when people ask what kind of research I do, I usually respond by saying I study consciousness, not that I'm a parapsychologist, because the word parapsychology is almost destined to go away eventually. The more we understand about what we're dealing with, we don't need the word para anymore. And it's probably not psychology either, although it's partially psychology. So this notion that you could use physics to study something about the fundamental nature of consciousness is not new. In fact, here's Nicholas Geeson's group back in 2009, basically saying the same thing. Let's use some element of being human to participate in a physics experiment. And he's proposing using human eyes as detectors in an experiment, which I think is completely the wrong direction because human eyes are physical. And he's conflating the notion of a physical eye with consciousness, which may or may not be true. So there's 2009. Here we have yet the same kind of proposal in 2016. So physicists do make proposals of this type, but basically nobody outside of parapsychology has gone ahead and tested it. And the reason is that if you're a physicist, especially in standard academia, and you do that, your colleagues will immediately say you're not doing physics anymore. And it's dangerous to do that if you're trying to be an academic. So this argument has gone on a long time. In fact, if you go all the way back to the origins of quantum mechanics, Max Planck, the person who came up with the idea of a quantum, said, I regard consciousness as fundamental. And this wasn't a mystical insight of his. The reason he said this is because all of the founders of quantum mechanics started to wonder, what is the difference between a physical system and a mental system? If neuroscience is correct, and consciousness, as we all enjoy it, is an effect of brain function, a side effect of brain function, well, then it should be describable by quantum mechanics because it would be a purely physical system. The problem is that it doesn't work that well. In fact, it doesn't work at all, as I'll describe in a minute. So Max Planck thought about this deeply and came up with the notion that maybe consciousness is fundamental in some way and, in particular, not physical. Erwin Schrödinger came up with the same idea. It's absolutely fundamental in some way. So did Arthur Eddington. In fact, almost every one of the founders of quantum mechanics ended up with the same notion. There's something peculiar about consciousness that doesn't seem to be admitted into the equations of physics. And this hasn't stopped. This picture is showing people from generally the 1920s. Here we have 1950s up to the present day. All well-known physicists, all coming to pretty much the same conclusion, that there's something important and peculiar about consciousness. So, physics and the non-local mind. And in order to understand what I'm talking about here, we need to know something about what non-locality means. So here's one way of thinking of it. We live in our everyday world in a classical domain. Each of us feel like separate entities. You're over there, and I'm over here, and we're watching the clock, and it's ticking. So this is the classical domain of physics. We see space and time, we feel separate, and things are independent of observation. So in a psychological sense, that's not true. I am behaving differently because there's a lot of eyes looking at me. But if you were to look at this glass, then from a classical physics perspective, this is not going to change just before you're looking at it. That's classical physics, it's common sense. So, let me put this back on. Okay, so that's common sense. This is what I would say is the realm of ordinary conscious awareness. That's everyday consciousness. But we all know from many different realms, from psychotherapy and the neurosciences and hypnosis and on and on and on, that there's a much deeper side to your conscious awareness, the unconscious, the subconscious, and even deeper. So here we can now start thinking of the transition between the everyday classical world of physics and the quantum world. It's a deeper world. With the moment you get below the surface, you start seeing concepts like interconnectedness of all things. You see observer dependence. You see that these effects do not occur in space and time. They occur outside of space and time, which is very difficult to wrap your mind around in, because our language and our everyday experience is in space and time, but not the moment you get out of the classical domain. So this is also the domain of the unconscious. You can start seeing a parallel here between physics and between the psyche. If you go below the quantum domain, which is the leading edge of physics now, we might call it the post-quantum domain or the supra or the super-quantum domain. It's extremely abstract, both in terms of the mathematics that are used to describe it, and many physicists and mathematicians are beginning to think that ultimately, as far down as we can imagine going, we're dealing with information, not energy or matter anymore, but information or mathematics or symbols. It's so abstract that we don't have the proper language really to talk about it. Well, if you go on the psychological side now, we're talking at this deep level. This is where mystical union happens, where a yogi might say it was samadhi. A person from the esoteric traditions would talk about gnosis. It's this deep level of knowing where the distinction between mind and matter basically disappears. There is no distinction anymore. So just to emphasize this point, classical physics, there are three principles which describe what that is. It's locality, reality, and causality. So locality is that things work by banging against each other. So in order to have something make something else happen, it has to bang into it. Reality is the notion that real objects have properties. So if we describe a glass, we'll describe it in terms of its weight and its material and lots of other things, and it's stable. It's like it has these properties. In fact, it's very difficult to think of objects that don't have properties. That's like our notion of everyday world. And causality is very similar to locality, that the way to make things work is to bang against them, either with particles or force. So in the quantum domain, oh, and by the way, here's a sign. In case of fire, exit building before tweeting about it. Because classical physics in many ways is a refinement of common sense. So this sign is basically reminding common sense. Leave first, then tweet, except for President Trump. So when we go to the quantum physics domain, suddenly we have non-locality. Things can happen without actually being near each other. Quanta have no properties, which is one of the reasons why it's considered so weird. How can you talk about a thing that has no properties? But that is the case when you talk about unobserved objects in the quantum realm, and things can happen without ordinary cause. So all of the things that we consider to be part of the everyday world, part of classical physics, go away completely as soon as you go down into actually just slightly below the realm of classical physics. And by the way, quantum physics is not the end of everything. It's been around and very healthy for 70 years or so, 70 to 80 years, extremely precise in terms of how good it works, but that's not the end of physics. And we know it's not the end of physics because the mind can do things that can't be accounted for yet by quantum mechanics. So there's my picture for quantum physics. So non-locality then, from a physics perspective, is talking about both information and causation that are unbound by space and time. So now we go to Nature to demonstrate, Nature magazine, to show what happens with one of the strange things about entanglement, which is a quantum phenomena. And this is a way of demonstrating that what appears to be separate particles are in fact not really separate. So you take a silhouette of a cat, and now you're going to take two separate particles of light, two photons. You're going to shoot one at the cat, and you're going to shoot one separately, and they're going to go onto a screen. So in this case, what you would expect to see for the cat is the outline of the cat plus maybe a little glow around it and just a splotch of light. But in the quantum world, if you're using photons that are entangled, this is what you actually get. The one on the left are photons that are being blocked by the silhouette of the cat, but the other one are photons that never touched anything. They show a cat shape because their properties are being influenced by the photons that touched the silhouette. So this is a very dramatic way of showing that even though the two photons seem separate, they're sharing something, they're sharing properties. So this is very unlike the classical world, except for the possibility of something like telepathy. You have two people, very isolated, may not be anywhere near each other, both sharing something, emotion, thoughts, something at the same time, with no apparent causal connection. That's what makes it seem so strange. The other thing in quantum mechanics that makes it very odd is that it is sensitive to observation. So the way of thinking of it is that physics deals with the objective world, but we have subjective experience. Our conscious awareness is subjective. And in this observer effect, we're talking about a blurring between the objective and the subjective. And by the way, I'm trying to speak slowly. This is slowly for me. Because I understand the language thing. But when I get excited, I start speaking even faster. So when I see people either nodding off or getting puzzled looks, I'll try to slow down, but it's hard for me. So here's how we know that observer effects exist within quantum mechanics. You take a very simple device like a double-slit optical system, and you shine a light, a photon, that'll go through one slit or the other. And not surprisingly, if you do this again and again, you would expect to see two bands of light. And in fact, if you're looking at this and you're measuring where the photons are going, you will indeed end up with two bright bands of light. So far, this is not surprising at all. It's light behaving like particles, photons. In fact, on the screen, you will only ever see little pinpoints of light. You don't see things wavy, you see only points. So this seems normal. Where it becomes unnormal is if you don't know which of the two slits the light goes through. Then what you see on the screen is not two bands of light, but an interference pattern, which is exactly what you'd expect if a photon was a wave. So this is the observer effect demonstrated in an easy way. So here's the interference pattern. So the question that we're asking is, well, what if you have a meditator and you ask them in their mind's eye to see which of the two slits the photon goes through? Would that do anything? This is, in a sense, what Geeson and the other physicists who are thinking about this is what they really want to do, but it's too dangerous to do. So us parapsykologists get to do it. A physicist would ask then, what causes the quantum wave-like potential to transition into classical particles? As I already mentioned, that there's something peculiar about observing the system that makes it change its behavior, almost as though light was shy of being observed. So John von Neumann was the mathematician who put the foundations of quantum mechanics on a firm basis in a book by that name, Foundations of Quantum Mechanics. And he was thinking very deeply about this notion of measurement or observation of a quantum system. He came to the conclusion that we need an extra physical factor in order to cause quantum wave-like structure to become classical particles. So by extraphysical, he meant consciousness. He didn't exactly say that, but when you read what he wrote, he meant that, because that's the only thing he could have meant. So this is then talking about the wave-particle relationship of light and quanta of any type. It looks quite peculiar. It changes, depends on whether you look at it or not. And it brings us to non-local mind. So non-local mind, by that I mean information and causality that are unbound by space or time. That's in a way of using language of physics to talk about basically any kind of psychic or mystical experience. So psychic phenomena we talk about in general, extrasensory perception, clairvoyance, precognition, all of that stuff. That are non-local connections through time and space. That's what it is. And psychokinetic effects are objective and subjective realities becoming blurred. So you already see that we're beginning to develop a parallel between an understanding of quantum mechanics, and by the way, all of that is not controversial. That's all mainstream in physics now. Where it becomes not mainstream is connecting it to consciousness, and even more so, connecting it to experience, suggestive that we can somehow experience quantum-like phenomena. It's controversial because we don't know how that can happen yet, but the parallels are there. So we have non-locality, which is a quintessential characteristic of both quantum phenomena and psychic phenomena. And the question then is this parallel meaningful? Is it a coincidence or not? Many physicists would say it is a complete coincidence, that you're trying to explain one mystery by using another. And I would say, I don't think so. I think it's a parallel that's worth looking at in more detail. So here are parallel lines. We just put some blocks here. It's still completely parallel. When I take the lines away, it doesn't look so parallel anymore. This is a way of illustrating that your perception is strongly biased by the surround. So if you're brought up in standard physics curriculum, your parallel lines will be different than somebody else's parallel lines, and you see things in a different way. Well, I was trained both in physics and electrical engineering and in psychology and in music. I have roughly the same amount of training in all of those fields, so I'm very comfortable with multidisciplinary thinking in the academic world. Multidisciplinary thinking is not very popular for a good reason, though, that the academia and science has carved up science, or carved up the real world into little pieces. That's what disciplines are about. So in the academic world, you have to be evaluated within your discipline. And if you happen to be doing something which also requires that discipline, which might be incredibly creative, nobody knows how to evaluate it. So not only will you not get tenure, you'll probably get fired at some point, because it's too strange. The other thing that happens in these kinds of discussions is we can talk about theory and possibilities, but where's the evidence? Does anybody know who this is? Dorian Nakamoto? He's the person that's credited with developing Bitcoin. And he was being charged with something and wasn't very happy about it. So where's the evidence? Well, we can start looking for evidence like this. These are macroscopic psychokinetic phenomena, except in this case, of course, it's a trick. It's a well-known levitation type trick. It's called a suspension. My wife took this when we were visiting Paris a couple of years ago. Or we can go back all the way to the 17th century with Sir Francis Bacon, who was one of the early scientific pioneers who put the basis of empiricism to become part of science. So what Bacon said was very interesting. He said to test the force of imagination, you could toss dice and use statistics to see whether the mind, which is using force of imagination, what we would call the will, you could see whether the will does something in the real world by tossing dice and seeing what happens. So he was 300 years ahead of J.B. Rhine from Duke University, who in the 1930s started doing this. It would toss dice and have people try to get numbers of ones or twos or whatever to come upwards. At the same time, in Sweden, Håkan Forwald was doing similar tests with dice, except rather than trying to get numbers to come up, he would roll them down an incline like this and have people try to make them move to the right or move to the left. So they're contemporaries in doing this research, and both of them found evidence that you could do that through the force of will. So Francis Bacon was right. He just was too far ahead of his time. Starting in the 1960s, Helmut Schmidt started doing experiments to refine the notion of the dice tossing experiments. And he used devices based on quantum properties, where it was either radioactive decay times or the use of something called electron tunneling. So here he is with his daughter using one of his early machines that he made to see if the mind could, in fact, go down into the quantum domain and start mucking about with the probabilities. So electron tunneling works like this, and the reason I mention this is because this is the basis of most modern devices called random number generators that have been used to test these kinds of ideas for a long time. So electron tunneling is, you imagine that this ball that the person is pushing up the hill is like an electron, it's a particle. And electrons definitely have particle-like characteristics. They have certain charges and you can measure them. And the hill represents an energy barrier. So the electron has a certain amount of energy, you're trying to push it over this energy barrier, and it takes a lot of effort to do that. Sometimes it's so high you can't do it. So that's a particle-like electron, but electrons are quanta, and so they also have wave-like characteristics. So it turns out that waves are not like water waves, they're waves of possibility. And because it's a wave of possibility, they can do virtually anything. Some things with very low probability, but nevertheless they can do virtually anything. They can be here and then disappear into another galaxy in the next minute. So if you take a semiconductor and you take advantage of the wave-like characteristic, the question is, it's called tunneling because the electron can occasionally tunnel directly through an energy zone that it otherwise would not be able to go through if it was just a particle. So can the mind help it do that? Can it adjust the probabilities to make it more likely to tunnel through this zone? So this is used in these kinds of devices, random number generators, to create the equivalent of coin flips, random sequences that are fundamentally random, according to quantum mechanics. Because the underlying reason for why you're flipping a coin one way or the other is due to things like tunneling, which is a quantum phenomenon, and supposedly unpredictable. So we take these random bits, we keep track of the zeros and ones, and it creates a random walk over time. And now you give somebody instructions for their will to make it produce more ones. And if they were successful, then you'd get a deviation. And if it was successful long enough, you'd end up with a statistically significant deviation, showing that your mind is able to influence the quantum domain. So here's Bob and Brenda Dunn from Princeton University. They ran a lab that went for about 27 years at Princeton, and they did an experiment very similar to this. They'd asked people to mentally aim high to produce ones, to aim low to produce zeros, or to withdraw their attention and just see the baseline. And they got results that confirm that that's what happens in thousands and thousands and thousands of trials. So they published it in a pretty good mainstream physics journal, Foundations of Physics. And basically, the reaction was like Bruce Lee here. That reaction was, yeah, but no one could replicate it, so it's probably a mistake. Because you can imagine if you're coming out of an engineering department at Princeton University and publishing in a mainstream journal, you would think people would get all excited about it. No, because it can't possibly be correct. So at the time, I was at Princeton as well, and we decided to see whether it was true that this lab was the only one that was able to get this effect. So we looked through the literature from 1959 to 1987, which is when we did the study. We found 152 publications by lots of investigators talking about many experiments and many controls. My colleague in this is Roger Nelson, and we published it again in Foundations of Physics. What we found was that for all of the studies that involved no mental push, these are calibration studies, you end up with something that looks very much like a normal curve, meaning that it's behaving like actually a binomial curve, but it's behaving by chance. But if you look at the studies where people are mentally trying to push the system, you end up with over a 7 sigma result. That's associated with odds against chance of beyond 1 trillion to 1. So something happened when people are looking or willing at these electronic random number generators. It was quite clear. Some time passed, and then in 2006, some German colleagues published a subset of studies that brought it up to date, these psychokinetic studies. And they concluded that the overall effect size was somewhere between a z-score of 4 and 3.59, which translates roughly into about 10,000 to 20,000 odds against chance. They then proceeded to dismiss that effect as an artifact, but nevertheless, this was their own conclusion as to what was seen in lots and lots of studies. And that was published in Psychological Bulletin, which is a mainstream journal too. So over the years, I've done studies involving random number generators, the effect of intention on water structure, the effect of tea and chocolate that had been intentionally imprinted by senior Buddhist monks who were attempting to bless it. And then we did studies to see whether people under double-blind conditions could tell whether they were getting the blessed tea or chocolate or a controlled tea and chocolate from the same batch. And the short answer is yes, they could. We also studied the effect of intentionally blessed water on the growth of seeds, and we got very strong results there. The effect of distant healing on cell cultures, distant healing on human physiology, and the last two categories that I'll talk about in more detail are double-slit optical systems and entangled photons. So this is what I've been working on the last 8 years or so. So in each one of these cases, regardless of the type of target, you can go all the way back to Francis Bacon, and we're testing the force of imagination, the force of will, and it does things to physical systems. You have to be careful on what you're measuring in the system, but you can see effects. I also want to mention just briefly that some of our studies are funded by the Be-All Foundation, which is a foundation part of a Portuguese pharmaceutical company called the Be-All Company. The Be-All Company is really unique in that the founder was interested in parapsychology and had a biennial competitive grant for studies in parapsychology. In fact, it's the only worldwide granting organization that funds parapsychology. So we've gotten a number of grants over the years. The Be-All Foundation, as a pharmaceutical company, among other things, produce medicinal suppositories. And if you ever get to go there to visit, you should see their hall of suppositories in a museum, which is quite interesting. So one of the things that the Be-All Foundation allowed us to do, which is just about to come out, is an iPhone app called PsyQ, which is the psychic measuring equivalent of an IQ. It's a series of, in this case, 3 tests that you would take on your iPhone, and we keep all the data, and lots of data actually behind it. It has a precognition test, 2 types of precognition tests, and a psychokinetic test. So the smartphone allows us to generate truly random numbers, so we'll be able to see whether people can influence the random numbers being generated on this app. The other thing is a bigger project called PsyGenes, which we're doing in collaboration with a professor of genetics at Stanford University. And this is looking to see whether a common report is that psychic ability runs in families. So we've worked with lots of people over the years who claim to be psychic or mediums or something, and we always ask them, does anybody else in your family report this? And almost everyone says yes. My mother, my aunt, sometimes it skips a generation, their children, so on. So we're looking for a genetic component. And the way we're doing this is we surveyed 3,000 people, and we ended up with 10 that we selected out of that, where people who were psychic, who we vetted to be psychic, we were able to demonstrate that they were psychic to our satisfaction, and they came from families that report psychic ability, and they were willing to give us their DNA. So we got then matched them by 10 people who report no psychic ability in themselves or their families, but their age and gender matched. And we got their DNA. We gave them to our buddies at Stanford University as part of a larger pool of looking at people who report exceptional experience of all kinds. People who've had UFO contacts, who've seen fairies, who, you name it, the whole range of strange things, but only in people who are assessed as being extremely credible. And that this credibility thing is important because lots of people say they see UFOs and talk to fairies, but unless you have some reason to believe that they're not making it up or not delusional or a psychiatric case, it's difficult to know from afar. So almost all of the cases here are government employees with top secret clearance or other types of clearance who are in positions of extreme authority. And the reason why this is being done now is to find out if you have somebody who's operating nuclear weapons, for example, and they also talk about talking to the fairies, you want to know what to do with them. There aren't that many people who have the training and the ability to do it, and by every other psychiatric means of looking at them, they seem normal. So we're looking then at this variety of genes, and it's not a single gene. It'll be a very complex constellation of genetics, we think, that distinguish people who have those kinds of abilities, which are pretty far out on the schizophrenic scale, but not schizophrenic. So it's called the schizotypy scale. They're high out on that, but they're still completely normal, and we need to understand why that's happening. So we eventually may find that some people simply have a genetic mutation or a genetic difference, and if that is true, then through use of pharmaceuticals or other methods, we may be able to enhance it, or we can decrease it. And the decreasing side probably is more important than the enhancing, because most of the people who contact me want the psychic stuff to go away. They're disturbed by it because they can't control it. And I suspect that some proportion of schizophrenics fall into that class. They're extremely psychic, but they can't control it, and it drives them crazy. So we want to find maybe a different kind of treatment for people suffering from that kind of problem. So that brings us to Schrödinger's cat. So here's Schrödinger's cat in a box, and you're probably familiar with this idea of what observation does to kitties in a box. So you have a vial of poison in a box that's either broken and the poison came out, or it's not broken. The box is sealed, so you don't know whether the vial has been broken or not. And you use some kind of a quantum process to determine if it should break over a period of time. The usual way Schrödinger talked about it in terms of radioactive decay timing as a way of doing this. So since from a quantum perspective, the cat is both alive and dead before you look at it, it's in a quantum superposition of two possibilities, the question arises that if non-local mind can gain information from a distance by clairvoyance, well, maybe you can look into the box with your mind and save the kitty. So that's an experiment that we did. And no cats were harmed in this experiment. So we used a Michelson interferometer instead of a kitty. So what it looks like is this, looking kind of from the point of view of the laser. You have a laser beam coming out, goes through a lens, it goes through a half-silvered mirror, it bounces off two regular mirrors, goes back into the half-silvered mirror, and then it creates that concentric circle. That's an interference pattern. So that's showing the interference pattern that you get if you don't know which of the two arms of the interference of the interferometer that the photon traveled through. So if both arms, and when I'm talking about an arm here, is that an interferometer has two arms. It could be two slits. It has two somethings where light is interfering with itself. So the two arms open in this Michelson interferometer will give you this rippley pattern, an interference pattern. If you close one of the arms, you just put your hand in the way, then you get this smooth pattern. So we have a way of distinguishing if something is blocking one of the beams. So the experiment looks like this. The interferometer is inside a shielded room. It's sealed, so no one can see in there. You take a meditator outside. You show the meditator where to put their mind in the box so that it will block one of the beams. And if it does that, we have a very clear prediction about what's going to happen. And we have a camera that's sensitive to single photons that's able to see what kind of interference pattern are we looking at in this experiment. And the protocol is very simple. For 30 seconds to a minute, the instruction is now put your mind in the box, and now take it out of the box, and now put it back in. You do this back and forth. So for a calibration test, you do the same experiment with nobody observing anything. You just run it to make sure the equipment is working right. And this is showing the difference in the interference pattern between observe and rest. And there's no difference. So we know the machinery is working right. When a meditator does it, it doesn't work that way anymore. You're getting a rippley pattern, in this case upside down because of the way they did the mathematics, but the rippley pattern is saying that the interference pattern has changed from the way it was before. And this happens to be, he's no longer with us, but it's Swami Veda Bharati, who has an ashram in Rishikesh, and comes from a Himalayan yoga tradition where they developed the siddhis, the special yogic powers. So he thought he might be able to do this, and he did. we had meditators and non-meditators do this experiment. All the action was in the meditators. That group of 6 people ended up with odds of about 100,000 to 1. And the non-meditators ended up with chance results. So they gave us a clue right from the get-go here that it wasn't as though they had magical abilities, but they were able to do the task. Because imagine the task where I say, put your mind inside this box and leave it there for a minute. Well, if you have attention training, you can do that. At least you can begin to do that. If you don't have attention training, you can do it for about 3 seconds, and then you will start dreaming about hamburgers. So we tend to use meditators or people who have some kind of attention training simply because they can follow directions, at least the directions that we want. So we published that in 2008, and then we decided to take the next step and actually use a double-slit optical system. We didn't initially do this because the size of the slit in these things is 10 microns. 10 microns is 10 millionths of a meter. It's so small you actually can't even resolve it with your eye. There's 2 slits, each 10 microns, and they're 200 microns apart. So if I hold it up to the light, you can see light coming through it, but it's very difficult to resolve one or the other of the slits. So it's very simple. It's a laser, a filter to cut down the intensity, the double slit, and a camera, all in a line. And all we do in this is, again, ask a meditator to imagine that they could tell which of the 2 slits that the photon goes through. That's the task. So here I am putting together the apparatus, and the left side there, that long tube, is the laser tube. That was a helium neon laser that we were using. This is what the camera looks like. The camera is called a line camera because there are 3,000 pixels in a row, just one line of pixels, because all we care about is the intensity of the interference pattern. We don't care what the rest of it looks like. That's what it looks like when it's put together. This is what the camera sees. It sees alternating bands of light and dark. This is the interference pattern that you would expect to see if no one knows what's going on in the double slit. And then from a computer point of view, we plot the intensity level. So we use curves that look kind of like that intensity. The other reason for using a double slit system is that we know the mathematics of this very precisely. So you can model this mathematically, and this is called a Fraunhofer approximation. With the equations in, you can model every piece of the apparatus, and then you could use that to, and this is what the equation looks like. There will be a quiz later. So you can model, you can fit the predicted mathematical model against what we're actually seeing. And it's a very close fit. In this case, it's not exactly the same because whenever you use a real physical system, it's not going to be as ideal as the mathematics, but it's really close. And this is good because it allows us to, if we get an effect, we can use the mathematics to deconstruct what happened. And we can do that in a way that you can't directly measure, but you can see in the mathematics. So the protocol was like the other experiment. We compare the double slit power, how much interference there is, while people are observing versus not observing. And they did it, in this case, 30-second periods, and they repeated it, and the measurement of interest is how is the change in the interference pattern. So we did a bunch of control tests, and then we finally did a formal test based on what we learned. And if you remember that Geeson said if somebody does this and gets a surprising result, the reward is enormous. So we did the experiment. There was a control result. There's our experimental result. It's about 5 sigma, for those of you who know about such things, close to 100,000 odds against 1. This is a very surprising result from a conventional point of view, but we didn't get any reward. It says, he said, the reward is enormous. We're still waiting for our reward. But anyway, we went ahead and published it in a physics journal, and at that point in 2012, some people read it, we knew, very little feedback on this. But one of the pieces of feedback we got were people who were concerned that maybe what we were seeing in the lab was caused by the heat of the body itself. Those experiments were done in a laboratory where the person is 2 meters away from the optical system. And interferometers are exquisitely sensitive to everything. So we had this notion that maybe what was happening is that when you get instructions to put your mind in the box to imagine what we're seeing, that people would lean a little bit closer to the apparatus. And they were told to withdraw their mind, they would lean back. So you're only leaning a couple of inches, but from the interferometer's point of view, it might change by 1/10,000th of a degree Fahrenheit or centigrade. So we decided we needed to test that. So we created a system where the whole experiment was done online. So now that nobody was ever close to the apparatus. In fact, the closest was 1 kilometer, and the farthest was 18,000 kilometers away. So there's our optical system. There's a web server. We had lots of people try this. And we also programmed a robot, a Linux system, to simulate a human user. Because the apparatus is sitting there, the server says, send me data. So it sends data. But it doesn't know whether a human has asked or whether our simulated human has asked. This gives us a nice way of testing the difference between human consciousness observation versus a Linux system. So people who use computers a lot might think that a Linux system has some degree of awareness. But I'm guessing that if it does have awareness, it's probably a lot less than human awareness. I hope. That was our hope anyway. So this is, somebody would go to their browser and they would see this big blue square and be told to please relax, which means withdraw your mind from the system. And then they would see a line moving on the graph in real time, which reflects how much interference is in the system. Their task is to mentally try to make the line go up, which would mean that they're interfering with the system. And for the Linux system, it was exactly the same thing, except it wasn't a person who was asking, it was a machine that was asking. So this is the results of the experiment through the calendar year 2012, about the same number of trials by the machine and the humans, and without going into great details on the statistics, there was a very clear separation. We saw a non-significant overall effect with the Linux machine and significant deviations with people, and we published this too. We did the same experiment again, 2013 and 14, 2 full years, and again even got a stronger result because we had more data this time. And we were able to look at where people were when they did the test. So these are little dots where each individual was when they did the experiment, and this allowed us to then see how far away from our laboratory they were when they were doing the experiment. It's hard to see on this kind of map, but we're in California, and South Africa is as far away as you can get from us. It's 18,000 kilometers. So we plotted on a graph then the effect size for each session, and the green would be an effect size of 0 on average, no effect at all. And this is what you predict would happen, but the red is what we actually got. So these two are significantly, the green and the red lines are significantly apart from each other, and more importantly, the slope of the red line is completely flat to 6 decimal places. What that means is that the observer effect is independent of distance. So this is what we would expect if we're dealing with some aspect of non-local mind, because it's non-local in space, it's also non-local in time, but it shouldn't matter where people are. And in fact, it didn't matter. So then people started paying attention to our papers, and one person said, well, how do we know this is really a quantum effect? Because we had been using lasers that are putting out a huge number of trillions upon trillions of photons per second. And so it's possible to think of this maybe in classical terms as a statistical effect rather than a quantum effect. So we thought, well, that's a good criticism. So we need to use 1 photon at a time. And another criticism was, how do we know that people are really doing the task, especially online? You don't even know if it's a human on the other side, or whether you started a program and then you walk away from it. So these are good questions. So to answer skeptical baby and skeptical cat, we got a new system which allows you to do a double slit experiment 1 photon at a time. And so that's what it looks like. And you can, it's the same kind of apparatus, except 1 photon. We also then took 32-channel EEGs of everybody doing the experiment, and see how happy our people are. They're all very happy. I'm not quite as happy in my picture. And we did this because you can look at a correlate of brain activity in terms of whether they're paying attention or not. At least we would know that they didn't fall asleep. So here's an example of what you see in the EEG. This is collapsed over all of the, in this case, there were 22 people in the experiment. It's looking at the alpha frequency. So let's see if I put it. So at that point there, the computer says, get ready to concentrate. And 5 seconds later, they would be told, now concentrate. So at the point of concentrating meant to put your mind in the box. That's what that meant. So what we hoped to find was at the moment that they switched their attention there, that we'd see an effect called alpha desynchronization. This is looking at the alpha waves in the brain that suddenly become scrambled, which is a well-known effect of shifting attention. And so we expected that you'd see a big change all throughout the brain, and in fact, that's what you see. There's a big change in alpha frequency. So it indicated at least that they were paying attention. We still can't tell that they're doing the task that we wanted them to. We asked them, and they said yes. And we know that their brain was doing the right thing, but other than getting a subjective report, we don't have a way yet of telling that they're doing exactly what we want them to do. I also want to point out this thing. This is a little Buddha statue, which we put on top of the, actually it's on top of the apparatus right above the double slit. This is linked through to the behavior of the device so that if the interference pattern changes, the Buddha will become illuminated. It'll literally get brighter because the LED starts getting brighter. So sometimes we give feedback like this because if I try to tell you to do an abstract task, it's hard. You start thinking about it, and we don't want you to think about it. So instead we'll say, make the Buddha light up. That's your task. That's all you need to worry about. Because if you do that, you will get the effect in the apparatus that we want. And this is also a way then of connecting you with the system because the feedback is real time. So if you're able to do this in real time, you're doing exactly what we want you to do. This experiment was done in complete darkness. And the only way that you can get the Buddha to get any light in the chamber was to get the Buddha to illuminate. So that was another motivation because people don't like to be in complete darkness. So this is the interference pattern that you get one photon at a time. We focused people's attention to what's called a trough, this low point in the interference pattern. And if they were successful in changing the interference, then more photons would show up in that spot. So we did the experiment, and sure enough, we got a significant increase in photons at that location, which is what we were hoping to see. So this showed that the effect was not a statistical effect, or not like a stochastic effect, but rather it was a quantum effect because it was operating one photon at a time. So we published a series of papers from 2008 to 2016, started to get more interest then. And we did a meta-analysis to look at what was the effect overall after 8 years of doing these experiments. And I'll skip over some of the details and just say that by combining the experiments, we can get either a liberal or a conservative estimate. Depends on your assumptions that go into it. So somewhere between a probability of 10 to the minus 5 to 10 to the minus 17th. So these are pretty healthy results over many experiments in 4 different kinds of double-slit systems, a single-slit double-slit system, and so on. So we finally were contacted by a French physicist who said, I don't know if I believe this, could I look at the raw data? Well, we're able to give him the data from our online studies from 2013 and 2014. It's 80 gigabytes. So we said, well, we could send you something, but it'd be easier if you just came here and we'd give you a disk. So he did. Came for a month and spent a month reanalyzing it and confirmed that our analysis was correct. And then another physicist, this one actually working at the Naval Postgraduate School, had the same question. Could I look at this data and just reanalyze it using my own methods and see if I get the same result? And he was able to verify it. So that was nice. Then we had a Brazilian physicist contact us and said he would like to replicate the actual experiment. So he came to visit us for a month to look at the apparatus, to see how we did it, and get advice on how we did it. And I gave him pieces of our equipment. I gave him the double slit, and I gave him a few other pieces. And he went off to Brazil, and here's the apparatus he made on an optical table, put the whole thing into a Faraday cage, had all kinds of fancy stuff involved in it. Well, I guess I'll say at this point that he did a pilot study which was successful, and just recently told me of a formal test, his first formal test, which was all pre-planned, which was also successful. And I wrote to him a couple of weeks ago and said, well, how's it going on your next experiment? And his response was that it no longer looks like this is an experimental result, but it looks like a technology. By that, what he meant is that the effect was strong enough that it was beyond the domain of simple statistics. It's like it was robust. So he put in some kind of secret sauce in this, which I don't know what it is yet. And we've been discussing the possibility of patenting the process, because you'd be able to turn this into what amounts to a intention detector. So that's something we're talking about. Whenever we do experiments, we, of course, have a due diligence list to make sure we're not fooling ourselves. So we ask lots of questions of possible other ways of thinking about the results. And either by design or by testing, we're able to rule out all of these other possibilities. And fortunately, independent replication is required, and we seem to have it. So that's also good. So what am I currently working on? So I did the double slit tests enough, and that I got to the point where I realized that the only thing I could do next was to encourage other people to replicate it. So there are people in Brazil, there are people in Berlin, there are a few people in Japan who have expressed interest. So far, the only one who's actually completed the experiments have been in Brazil. So I decided to keep going in this direction, but I didn't want to work with double slit systems anymore because I gave all my pieces away to other people. So instead, I decided to tackle this question of non-locality directly by looking at non-local mind and non-local matter. And asking this question: does consciousness interact with quantum entangled photons? Well, 15 years ago, if you wanted to do this experiment, you'd need a table that looked roughly like this. Very expensive, with lots and lots of optical systems, very expensive systems. 5 years ago, it would have looked like this. Now it looks like this. So there's a company in Munich that builds this device that creates very high quality quantum entangled photons in real time. And so we adapted this for use in our experiment. I'm pointing out here that there's polarizers that are in little motors, and the polarizers have to move around in order to get the measurement to show that it's entangled. And so here's what's happening inside the little white box. On the right side is a very intense blue laser. The blue laser sends out photons. It hits a special crystal called a beta barium borate crystal. And what the crystal does is occasionally, about 1 in every gazillion, 10 to the minus 20th or so, photon, it splits it from a blue photon into 2 red photons. And when that occurs, it spreads out in a certain direction. So these 2 red photons, the total amount of energy is the same as the blue one, except they're now 2 separate photons. But they have a strange property. As you know, when you put on polarized glasses, that you can see that light is polarized in certain ways. This is a property of light. So you use polarizers in this experiment in order to test whether the photons are actually entangled or not. So here's what happens. You have red light coming out. It hits mirrors. It bounces off the mirrors. It goes into polarizing lenses, which are on step motors. The step motors can turn different directions. And then they go through fiber optics out, and they go into this box. So this box is measuring the timing of the photons coming into the box. If they come in within 20 nanoseconds, then it knows that the 2 photons were produced at the same time. It still doesn't know if they were entangled or not, but they are at least a pair. So it's now going to look at coincidences in pairs, and this is what it does. So you have 2 photons coming in, and the polarizers could be at the same level. And if they're both the same, and the properties of the photons are the same, then you'll get 100% agreement. So you get a high coincidence rate. If one of the photons is coming in at a certain polarization, the other one is the same polarization, but the polarizer has been turned, you'll get no agreement. It'll block it. And you can do this for other possibilities too. You can get 45% agreement, 60% agreement, and so on. So you do this for all possible ways of doing 4 measurements, which ends up being 16 possible ways of doing it. And then you plot on a graph. On one curve is what was the position of the polarizer on the left, and the other one is the polarizer on the right. If these 2 particles were behaving like classical particles, meaning they're really separate, then you would get a line that looks like this. But if they're acting in a quantum entangled fashion, it looks like this. And what this means is that this is a stronger than classical correlation. It's sometimes thought that entanglement is extremely weak. In some respects, it's difficult to see in the laboratory, but it's actually stronger than a classical correlation. So this is the measurement that takes place inside this electronics box, and we know then that we're getting a certain number of entangled photons per second. Here's the method that's used. There'll be a quiz on this later too. CHSH is for Clauser, Horn, Shimoni, and Hult. No, Clauser, Horn, Shimoni, and Hult. These are the 4 physicists who came up with this particular method of measurement. It comes out with a very simple number. The number, it's called S, which is the strength of the entanglement. If these are classical photons, then the number will be 2, less than or equal to 2. If they're quantum entangled, it will be greater than 2, but less than 2 times the square root of 2. And the machine puts out an S value of around 2.5, plus or minus 0.05. So we know with very high confidence that these really are entangled photons that it's seeing. So here's what it looks like when you plot it over time. You get a value that changes over time. And we ask somebody to look at this, look at this S value and mentally try to increase it. So the protocol is very similar to other studies. We have periods of concentrate, periods of relax, back and forth, alternating. We're interested in the difference between the mean of the concentrating periods and the mean of the relaxed periods in terms of entanglement strength. There are 16 polarization angles. The step motors turn about every half a second. And so it takes 16 samples in order to get one full measure of S while you're mentally looking at the system. That means we have to lag the data by 16 samples. So we push it backwards. And when we do that, we then see that this is now an S value that is completely looked at by you. Because if you're only to look at one sample, then 15 other samples you may not have looked at. So you're not getting a full S value. So it's a little bit complicated, but that's just part of the design. So this is our first laboratory experiment. Here's our lag that I just talked about. The red line is a control. In statistical terms, this does not reach an area of interest, but the experimental results got a really good result. Here's chance down there. This is the point where things start to become interesting, and we ended up with actually a very interesting result, suggesting that the mind was increasing entanglement strength in the experiment. So that gave us confidence to go ahead. We ended up, and then because entanglement is non-local in space and time, the current record for entanglement over space is 143 kilometers. So we know that it works as far apart as you can get. Our apparatus is only this far apart, but you could in principle do it very far apart. So we put it on the web. So here's the apparatus. There's the kind of data it produces. It gets sent up 24/7 up to the Amazon cloud. And then the data is dumped into a server, or into a database. And now this allows us for a participant to go to a browser and pull data out of the system, and as many participants at the same time as we wish. And each of these participants is doing the experiment at exactly the same time. They're getting the data in real time, but all seeing the same result. So if you go to entangledphotons.us, on a smartphone, any kind of smartphone, any kind of PC, tablet, whatever, it will work, provided that you have JavaScript turned on. And it's running now. You'll get one of two types of feedback. You'll either get a line that you're asked to try to move the line up, aim up, or you'll get this particle cloud, which looks like a bubbling cauldron of little dots, and your task is to coalesce the dots into a circle. So if you do that, you're doing the task correctly. Both of these kinds of feedback are reflecting of the correlation strength between the photons. So here's the results so far of our online experiment. The blue is experiment, the red is a control. The first is with one person doing the test at one time. The second is 2 people at the same time, 3 people at the same time, 4 people at the same time. The blue line keeps getting higher and higher, and it's beginning to approach a significant lift, which is good, and the controls remain at a non-significant level. So this it's very similar to our double slit experiments, that whatever is going on here, even observation at very far distances, it changes the behavior not only of photons in a double slit system, but it changes the strength of correlation in entangled photons. That means that the non-local mind is doing something with non-local matter. So we didn't believe the result. We never believe our results. We always then trash it and build it up from scratch again, because if it's real, we're supposed to get a reward. And we're still looking for that reward. So we're going to keep doing it. So again, this is our version 2, where we started the whole thing over again, 1 person at a time, 2 people at a time, 3 people at a time. It's getting better and better. So it's beginning to answer a goal that we've often been asked about. If we have one person in the laboratory try to push something, well, what if you had 10 people? What if you have 1,000 people pushing it at the same time? It's very difficult to do that in the real world, because to get more than 2 people to do anything is practically impossible. So in this case, we'll be able to recruit people in dozens or hundreds or as many as we can get to do the same experiment at the same time and see what happens. And the reason why we want to increase entanglement strength is because there's the classical limit, there's the quantum limit, which our machine is producing very nicely. But if it goes to beyond 2 square roots of 2, if we get correlation strength that's too strong, it's called a supra-quantum effect. It means that it's going beyond orthodox quantum mechanics. And that would be a reason for physicists to take it very seriously that quantum mechanics is not finished. We need to go into something that is even more comprehensive, and the more comprehensive would have to include the mind. So that's actually the underlying strategy for why we're doing this. It's not simply to see whether it's changing the correlation strength, but can we push it beyond where current mechanics are living. Quantum mechanics, most physicists would say, would not predict that consciousness can do anything to it. So it's already a bit, it's not exactly a violation, but it's unexpected. But if we can go into this supraquantum domain, we should at least get like a hot fudge sundae as a reward. So to go back to our New Scientist article, experiments since the 1930s have repeatedly demonstrated that mind interacts with matter in various ways. Recent experiments by us and others suggest that they might be related in some way to quantum non-locality. But orthodox quantum mechanics alone is simply not radical enough. We think that at this point it's not able to explain what's going on. And it raises something like this, like, I'm going to another dimension, do you need anything? We need to like break out of the box and think in radical, crazy ways to try to come up with what's next. And the curious dog, of course, immediately asks, well, then how does it work? What is that other quantum mechanics? Well, as far as the quantum goes, I have no idea. But I do have a framework, a way of thinking about it. So it's similar to this. So you get this math problem, it says find x. So you know how to use Pythagorean's theorem, and you could do all that. But maybe you should take a completely different approach and just say, well, here it is. That's a correct answer. Find x. Well, there it is. And in general, first of all, it's not reasonable to throw away existing physics. Quantum mechanics works way too good, so that you don't want to just toss away textbooks. You have to keep it, but something must be missing. And if you think about the development of physics over centuries, we started with little models that worked, and then became more comprehensive and more and more and more comprehensive. And so present-day physics will eventually be seen as a special case, just like classical physics is a special case. And as we keep expanding, I think we're going to move into something like this. So we call things anomalous, controversial, like psychic phenomena, anomalous because the facts don't fit current theory. We're talking about the scientific worldview. So I'm going to give you a lecture for an hour about different kinds of ducks, and then I will talk about this kind of duck, which is seen sometimes, but sometimes you don't get to see it. And then I will give another hour lecture about rabbits, and I will show this rabbit. But then I'll remind you that that rabbit is exactly the same as this duck. So it's showing that some things are so ambiguous that unless you don't have the right context for what you're looking at, you may completely miss it, totally. So here's how I would propose a change. So here's physics, sitting at the base of what we think of as our scientific worldview, and there's chemistry and biology and psychology, and somehow consciousness magically arises at the top. This is reductive materialism. It's extremely effective. We do not want to get rid of it. It's just too good. None of this technology would work without it. But it gives rise to the notion that ultimately we're zombies, right? Consciousness is a side effect of this very mechanical process that starts bottom up. So we're zombies, and in this view, mind-matter interaction and any kind of psychic phenomena is simply impossible. There's no way to account for it, so it can't work. And you have people like Daniel Dennett saying we're all zombies. Nobody is conscious. So then I asked Daniel, and who said that? And his response would be, nobody said that. So you seem to have said that, and you're also very angry if people say you're wrong. So what's that about? Anyway, so this is part of the problem with the current scientific worldview, is that it's completely nihilistic. It gives a pointless universe. And you see this especially in younger students who start learning about physics. They get really depressed at this. It might be true that the universe is completely pointless and a nihilistic view is the way, in which case virtue becomes its own reward. That is a possibility. However, we have things like psychic phenomena which suggest that that's not the case. So we propose a different view, which is a lot closer to philosophical idealism. And all you need to do is take the existing scientific worldview and do this to it. We create a new basis. This, of course, is idealism. It's a notion that consciousness is fundamental in some way. It's the basis of a lot of Eastern philosophy. It's sometimes called panpsychism or neutral monism. This would suddenly allow mind-matter interaction not only to exist, but to be something that you could predict. Because what this means is, if something is happening below physics, meaning below quantum physics, it's not in space-time. So this consciousness, whatever we're talking about, is not this stuff inside your head. A little piece of it is there, but it doesn't exist in space-time. It's some primordial substance that emerges into the physics that we see, into quantum physics or sub-quantum physics and the classical world and everything else. So just as in physics you have electrons at that level, but you have it also in chemistry and biology, you have electrons everywhere, this would say that you have non-local consciousness everywhere. So we happen to be built in such a way that we're able to experience it, whatever that consciousness. It also suggests, though, that there may be nothing special about consciousness, and in a sense the neurosciences are correct. Our brain is constructed in just such a way that it allows this primordial consciousness to be self-aware. So it would please the neuroscientists, we don't need to change any of that, but it does question about what the origin of this consciousness is. It's like it's really deep in some way. So here are my collaborators. I don't do this by myself. We have lots of collaborators around the world. We have many people at the place that I work. Many funders have allowed us to do this. Some are individuals, some are foundations. At the Institute of Noetic Sciences where I work, we now have 7 scientists. We span a broad range of different disciplines, from computer science, medicine, neuroscience, molecular biology, more neuroscience, clinical psychology, and Lauren Carpenter in there in the middle. He's a co-founder of Pixar, the animation studio. He's the one who gave Pixar its name, and in the picture he's holding the top of an Academy Award, which he received for developing the CGI methods that allow you to draw natural scenes purely through computers. So there I am, and we also have a number of research fellows around the world, people like Rupert Sheldrake and so on. So what are my personal motivations? Sometimes I ask, well, why am I doing this? And it's a little bit like what Woody Allen would say, that I don't want to achieve immortality through my work, I want to achieve immortality through not dying. Or I don't want to live on in the hearts of my countrymen, I want to live on in my apartment. So it's not quite as bad as Woody Allen in this case, but I'm primarily motivated in this case by curiosity. I think like a lot of people, I would like to know what consciousness is too. All of the big questions that people ask about life and death and so on. This is a way of directly addressing these kinds of issues, which in other scientific disciplines that I've been involved in over the years, you're not allowed to ask those questions. So I figured, well, what am I doing then? You know, to provide meaning in your life, do something that you're really passionate about, and I'm passionate about those kinds of questions, and that's why I do what I do. So I'm going to end there, and I thank you for your kind attention.